So we introduced the BOREL-CANTELLI lemmas in the previous lecture. Let's remember them. BC lemma 1 talks about a sequence of sets that are not necessarily independent. Talks about that is a sequence of events A1, A2 from the same probability space with the probability of the set AI equal to Pi such that summation Pi, the sum of the probabilities converges. Okay. Then with probability 1, only finitely many of the AIs occur. Okay, so to prove this, we will use the continuity of probability. Okay, let B be the event that infinitely many AIs occur. Okay, so we'll show basically that the probability of B is 0. Okay, now we will define a sequence of sets B sub n such that B is the limit of these sets. So let B sub n be the union of AI I from n onwards. This means we take a certain number n, for example 11, okay, and then we take the union of events A11, A12, A13, A14, etc. So from n onwards we take a union. Therefore, as n grows, this union is a shrinking set in terms of n. Okay, and let's so basically B1 is the largest set in the sequence. B2 is smaller than B1. B2 is included in B1, in fact, and B3 is included in B2, etc. And let B be the infinite intersection of these sets. All right. Then by continuity of probability, the probability of B is the limit as n goes to infinity of PBN. All right. So, but notice that the probability of Bn we can compute. Well, at least we could bound it from here, right? Because Bn is nothing but the union of the events AI from n onwards. So by the union bound, which says that the probability of a union of events is upper bounded by the sum of the probabilities, we can bound the probability of Bn. Let's say union bound. Very loose but surprisingly useful bound. So the probability of B then, since this is true for all n, this is true for the limiting set B, probability of B must be less than or equal to the limit of summation Pi, I bigger than or equal to n. But notice that the sequence, the series is convergent. This is only possible if this limit is 0. Okay? Therefore, we showed that the probability of B, that is the probability that infinitely many AIs occur, is 0. This means the AIs will stop happening after a while, meaning finitely many AIs will occur. Let's prove BC lemma 2. the difference of BC lemma 2 is that it required independence. So consider independent sequence of events AI such that PI is the probability of AI, and the summation of PI is infinite, meaning the probability these do not sum to a finite number. Okay, then AIs happen infinitely often with probability 1. Now, let's pause for a moment and try to think of why independence is needed here. If we discarded the assumption of independence, what would change? Well, trivially, you can think of AIs all being the same event with some certain finite probability. In that case, if you sum up all the probabilities trivially, the sum will not converge. But does this mean that AIs happen infinitely often? Well, they're the same event. So that is why independence is necessary in order for BC lemma 2 to be valid. Okay, so let's do the proof. Okay, so again, we'll use the idea of continuity of probability. This time, a growing sequence of events. Let's define C as the intersection from 1 onwards, let's say k from 1 to infinity, of the union of the events AI, I from k to infinity. Okay, we can think of this as a set BK. Okay, and BKs, as k grows, BKs are growing. I'm sorry, as k grows, BKs are shrinking. Let's see. Okay. Here's the problem. This is not what I want to define as BK. Let me take this back. I want to work with not C, but the complement of C. So the complement of C using using the complement of C will be more useful here. Union of the intersection I from k to infinity of AI complements. Okay, now I can define BK as a growing sequence of sets. And I'm going to use continuity the other way. So B1 is a subset of B2, is a subset of B3, and so on. All right. Now, probability of C complement. Now, C, remember, is the infinite union of the B's. Okay. So this is the limiting set. Okay. The probability then is the limit as n goes to infinity of the probability of Bn. Okay, and this is this is by definition the probability, the limit of the probability of the intersection of AI complements I from n to infinity. Okay, and we're making n grow here. And this is where we're going to use the independence of the sets AIs. Note that as AIs are independent, AI complements are independent. So we can express the probability of the intersection of AI complement as the product of the probabilities of AI complements. So we can simply write this as the product from 1 to infinity 1 minus pi, and then let's notice the following. When p is a number between 0 and 1, 1 minus p is less than e to the minus p. Okay, so we can perhaps see it over here. It's a cute little fact. If p is between 0 to 1, this is how 1 minus p looks. And this is how, let's see, I'll take another color. Bad drawing. This is how e to the minus p would look if I was able to draw it correctly. But basically, we can use this here. This is less than e to the minus p. Therefore, the probability of C complement is bigger than or equal to product of exponent minus pi. This is pi, of course, I from 1 to infinity. But this is nothing but x of summation pi minus summation pi, but this sum diverges because of our assumption, and therefore the negative exponent goes to 0. Therefore, probability of C is 1, and we have proved BC lemma 2.